In the previous video, we developed a Python program to compute the derivatives of the area E with respect to the 12 weights W for our very simple neural network. We can summarize the entire calculation in this particular figure. Instead of plotting all the layers from bottom to top, we're now plotting all the layers from left to right. So the input layer, layer 0, is on the left. The hidden layer, layer 1, is in the middle. And the output layer, layer 2, is on the right. Except for the neurons in the input layer and the neurons associated with the bias neuron, with the bias term. All neurons now have one additional quantity inside of it, which is actually the delta value. Right, those red texts are the delta values. The two delta values, delta 21 and delta 22, are computed from the differences between the ground truth and the neural output times the derivative of the sigmoid function evaluated at the neuron's logit Z21 and Z22. The derivatives of the error with respect to the weights on the second layer, those DW2 terms, right? All those derivatives are actually given in those red texts. Those red texts are the derivatives of the error with respect to the weights, the 6 weights in the second layer. And the derivative is obtained by multiplying the neuron output, the y value, with the delta value. In the neuron, the blue arrow is actually connecting with. So the derivative with respect to W201 is obtained by multiplying W10 with delta 21. So dW201 equals to Y10 times delta 21, right? The derivative with respect to W202 is obtained by multiplying Y10 with delta 22. Right? It's the y value multiplying the corresponding w value, the delta value, that's connected by a blue line, by a blue arrow, right, for that particular, that's associated with that particular weight. Right. And the same is true for the derivatives with respect to W211. So that's W211 here, and it's associated with this particular blue arrow. Right. So the derivative of the error with respect to W211 just equals to the y value multiplied with the w value here. Right. So it's y11 times delta 21. So y11 times delta 21. Right. And then the derivative with respect to W212 is equals to right, y11 times delta 22, right? That's this blue arrow, right? y11 times delta 22, y11 times delta 22, that gives you dE over dW212, dE over dW212 here, right? And then the last two. So the derivative with respect to W221 is going to equal to this y value, y12 times delta 21. y12 times delta 21 gives you the derivative with respect to W221, right? And then the last one, the derivative with respect to W222 equals to Y21 times delta 22. Y12, not Y21, Y12 actually. Y12 times delta 22 times delta 22. That gives you dE over dW222. dE over dW222, right? So, and then the delta values for layer 1, for the neurons in layer 1, must be computed from the delta values in layer 2. And the calculation is actually quite similar to the calculation of the logit in each neuron when we did the forward calculation, except that the directions of the arrows were actually pointing backwards. So to obtain delta 11, we need to do a weighted summation of delta 21 and delta 22 with the weights given by the blue arrows, W211 and W212. Right? If we look at the expression for delta 11, that's right here, right? Delta 11 equals to delta 21, that's this delta, multiplying with W211 plus delta 22, this delta, multiplying W212, right? So it's just a weighted summation of the two deltas, right? But now the blue arrows pointing from the lower layer to the upper layer, right? But now I have added a red dashed arrow that goes from the upper layer to the lower layer. So the red dashed arrow goes this way. So it's gonna go from these two neurons pointing backwards towards this neuron. Right? So those red dashed arrows represent this weighted summation. Right? So delta 21 multiplying with this particular weight plus delta 22 multiplying this weight gives you delta 11, right? Gives you delta 11. But don't forget to multiply the derivative of the sigmoid function evaluated at this Z11, the logit, right? So it's actually the summation, the weighted summation of these two deltas with the weights given by these two weights, these two corresponding weights, right? And then multiplying the derivative of the sigmoid function evaluated at the logit Z11, right? So that's the formula for computing delta 11 from the delta values in the upper layer. The same is true for delta 12, right? To compute delta 12, we need to do a weighted summation of delta 21 and delta 22 with the weights given by delta W221 and the W222. Right, so it's delta 21 multiplied W221 here, plus delta 22 multiplied W222, and then don't forget to multiply the derivative of the sigmoid function evaluated at Z12 here. Right, so those red dash arrows that's pointing backwards indicates how the weighted summation is done for the delta values. Right. And then once the delta values for the neuron in layer 1 are obtained, the derivatives of the error with respect to the weights, with respect to the 6 weights in layer 1, is again obtained by just multiplying the y values, which is actually the x values, right? Because this is layer 0 now, right? Which is actually the x values. Multiplying the x values with the corresponding delta values, right? That's going to give us the weight, the derivatives of the error with respect to the weight, right? So once we fully understand how the calculations are done, we can easily generalize the backpropagation algorithm to neural networks with arbitrary complexity. Right? This is a very simple example, but the algorithm, the backpropagation algorithm that we just described, can actually be generalized to neural networks with arbitrary complexity. It's So all you have to do is to introduce some additional variables into every neuron that's going to store the delta values, right? In addition to y and z values, you need one more variable to store the delta values inside of each neuron, right? And when you actually do the backpropagation, you have to sort of pay attention to the indexes, superscript and subscripts, right? And then there is a weighted summation stage that's just like the forward calculation when you compute the logit in the forward calculation, right? The one additional thing that you have to do is to multiply the derivative of the nonlinear function that's evaluated at the logit value inside of that neuron, right? That's just the one additional thing that you have to do in order to actually get the delta values. Right? Once you got the delta values, the derivatives with respect to the weights are just obtained by multiplying the y value and the delta value that's sort of connected by the arrow, the blue arrow, that's associated with the derivative on which you are trying to get the derivative for. Right? So the calculation is again simple enough. Simple enough. It's really, if you actually account for the indexes, it looks like it's kind of complicated, but again, it's just multiplications and summations, and you need additional data structures to store those delta values. Right? And then all the rest of the calculations are just multiplications and summations, and you need to pay attention to the subscripts and superscripts, right? How you actually organize those numbers in the appropriate data structure is kind of important. Right? So far, we have been using just we have been using only one example, basically. We basically have using one example as our entire training data set. Right? The inputs, 12.5 and 4, and the ground truth outputs, 10 and 1, are for only one YouTube video that we are talking about. We have been talking about so far. And in practice, in order to actually obtain a neural network with any kind of a predicting capability, one training example is certainly not enough. We will need a large number of such training examples, and each example should have sort of 2 inputs and 2 ground truth outputs. These kind of examples can be used for doing this kind of a supervised training, the so-called supervised training, basically. So suppose there are capital N, this many YouTube videos, this many training examples, basically, in our training data set. And then for each example, we have an error, right? That's sort of the error between our model prediction and the ground truth values, right? Now we cannot just use E here because E actually depends upon the example, right? The example index. So here we use En, subscript n, this small case n. And small case n goes from 1 to 2 to up to big N, right? And the total error for the entire training examples in our training dataset can be obtained just by doing a summation over the individual errors for each of the training example, right? And then we call this summation En with the subscript in. And we can show that the derivative of En, the derivatives of En with respect to the weights, with respect to an arbitrary weights at an arbitrary layer, WLIJ, right, actually equals to, because En is just this summation, right? So it's partial this summation, partial WLIJ, right? And the derivative is linear, so you can actually put the derivative inside of the summation. So you can move the summation out of the derivative, right? You move the summation out of the derivative, becomes partial En, partial WLIJ, right? That's just a summation of the partial derivatives of En over the same weight, right? And we know how to actually compute the partial derivatives of one error, the error for one example with respect to the weights, right? So all we have to do is to compute the derivatives for every error in our training dataset, and then do a summation over all the training examples. Do a summation of the partial derivatives over all the training examples. Then we get the partial derivative of En with respect to the weights, right? So in principle we actually in principle we know how to actually compute these derivatives, right? It's just computing the derivatives of each individual error and then do a summation, and then we know the derivative of En with respect to all the weights. And once we obtain the derivatives of En with respect to the weights, we can again use the steepest descent algorithm to search for the optimal set of values for the weights. And this algorithm is known as the batch gradient descent, or BGD. In practice, the capital N can be really large, on the order of millions or even billions. So the total amount of calculations involved in calculating the derivatives can become prohibitive for problems of practical interest. And there is a subtler problem associated with the BGD. For BGD, the relation between En and the weights are fixed, right? Because the total number of examples in your training dataset, and all those examples are actually fixed. So En is a deterministic summation of all the En, right? And all the En are deterministic in terms of all the weights. They are all deterministic functions. So the relation between En and all the weights inside your neural network is fixed. Right? Suppose we have only one weight. That's the horizontal axis W, right? And then En is the vertical axis. And this gray curve represents the relation between En and W. We have a global optimal value, W value, that's indicated by this star here. And then there is a local minimum that's indicated with this X here. So if we picked a W value that is located to the left of this X as our starting W value in our steepest descent algorithm, then as we move towards this X location along the derivatives, along the negative derivatives, the value of those derivatives are going to gradually decrease, and at the X location, the derivative value actually becomes 0, and our steepest descent algorithm is going to stop iterating and return the W value that's at the X location as our optimal value. And we will have no idea that there is actually a beta solution that's located at this particular star, right? That's one of the weaknesses of BGD, because the shape of the curve is actually fixed, so which makes the BGD actually more susceptible to local minima. It's actually quite sensitive to local minima. If your starting value is not at the correct location, right, then it's very likely that it's going to get trapped inside of a local minima instead of converging to a global minima. Right? BGD is quite sensitive to local minima, and it is one of the weaknesses of BGD. Some of the weaknesses of the BGD can be addressed using the so-called mini batch gradient descent, or mini BGD. Right? And in this mini BGD algorithm, we do not use the entire example dataset to compute En. Instead, we pick a random subset of size capital M out of the entire training dataset for each iteration of the steepest descent algorithm. And this randomly picked subset is called a mini batch. The derivatives computed using this mini batch So E in now equals to a summation of En. That's for n that's inside of this mini batch, right? And this mini batch keeps changing. The index n keeps changing from iteration to iteration, right? Because it's randomly picked. It's a randomly picked m numbers, right? So the derivatives computed using this mini batch will certainly be different from the derivatives computed using the entire training data set, right? But the practice has, so experiences have shown us that if the mini batch is not too small, so it's still representative enough. So M is still large enough, basically. And through many iterations, the averaged differences between those gradients will not be significant, right? Through many iterations, you can actually average out the differences between the derivatives computed using the mini batch and the derivatives computed using the entire data set, right? So the mini batch gradient descent will certainly save a lot of computational resources if capital M is much smaller than capital N, right? Because that just involves a smaller summation over a smaller sort of example data set, right? And all the derivatives are kind of, the calculation for the derivatives is involves a lot less calculations also. Right? And in addition to this advantage, the mini batch gradient descent is also less sensitive to local minima than BGD. Because for every iteration, E in is computed from a different mini batch, right? So N is a different subset of this 1 to 2 to 1 to capital N. So E in is computed with a summation of different En for every iteration, right? So the shape of the E in W curve keeps changing from iteration to iteration. So for the batch gradient descent, the E in and the W curve is sort of fixed by this dark gray curve. But for mini batch gradient descent, this curve, the shape of this curve actually keeps changing from iteration to iteration. Sometimes it looks like that. At the next iteration, it may look like that. And at the next iteration, it may look like that. So the shape of the E in W curve or E in W surface, if W it's not just one W, it's got like many W's, then it's an E in W surface, right? So the shape of the surface is going to keep changing from iteration to iteration, right? And so by descending on this kind of a dynamic error weight curve or surface, we actually have a better chance to navigate around those local minima. For mini batch gradient descent, it has a less chance to get trapped inside of a local minima like in BGD, right? Because the E in W surface keeps changing from iteration to iteration, right? In the case that the capital M, when M equals to 1, the mini batch gradient descent becomes the so-called stochastic gradient descent, or SGD. But these days, the SGD are used less often than the mini batch gradient descent algorithm. The size of the mini batch, capital M, is another hyperparameter that needs to be adjusted based upon the specific sort of application. Right? The first hyperparameter we talked about is the learning rate. When we talk about the steepest descent in previous videos, the learning rate is the first hyperparameter that we talked about, right? And the learning rate basically controls the speed or the step length of the descent algorithm. Another question we need to talk about is why we need a neuron with output y equals to 1 at every layer of the neural network, right? Here we have 1 here with the output 1 here, right? That's actually an input layer in the input layer, but with L equals to 0 basically. That's another neuron with Y equals to 1, right? The question is why? Why do we need such a neuron at every layer, right? Don't forget that the logit Z actually equals to the weighted summation of the outputs Y from the lower layer. Suppose we now have just one output, Y1, from one neuron, and no bias term is added. So the relation between the logit in the upper layer and Y1 is just a straight line. So horizontal axis is Y1, vertical axis is Z, right? It is just a straight line that has to pass through the origin, right? It must pass the origin, because when Y1 equals to 0, Z must equal to 0, right? It doesn't really matter what value W1 is, Z must be equal to 0. So this straight line must pass through the origin of the ZY1 plane, basically, right? So if all the data points, all the observations, all the data points are actually clustered away from the origin, so a straight line that has to pass through the origin will actually never be able to provide a good fit to this set of data, because the only thing that you can adjust is the weight, W1. But by changing W1, you're only going to change sort of the angle of this particular straight line, right? But you can sort of see the angle, and for this green line, the angle of the green line and the trend of the data is already pretty close, right? But adjusting W1 is not going to sort of provide you a much better fit to this set of data. But if we add a neuron with output equal to 1, now the ZY1 curve is going to look like this kind of thing, right? Because Y0 equals to 1 now, right? So Z actually equals to W0 plus W0 multiplying 1, right? Plus W1 times Y1, right? It's 1 is 1 multiplied by W0 is W0, so it's W0 plus W1 Y1, right? So it's not W1 Y1 anymore, it's W0 plus W1 Y1, right? So it means that if we add a neuron with output equal to 1, now the ZY1 line is allowed to have a non-zero intercept on the ZY1 plane. Of course, W0 can still have a value of 0 if that provides a better fit to the data, right? But if the data are clustered away from the origin, a non-zero W0, a non-zero intercept, will allow for a much better fit. So by adding the neuron with Y equals to 1, we actually provide additional degrees of freedom for the neural network to better fit those biased data.